Okay, maybe let's start. Yeah, today is the last lecture, and so since the last lecture, we talk about how to determine the gapless states from the symmetry. The main idea is that the symmetry is not described by group, or actually it's not best described by group. And it's better to describe symmetry using so-called topological order in one higher dimension, which is the same thing as a so-called categorical symmetry. So for 1 + 1 dimensional symmetry, the topological order in one higher dimension, that's in 2 + 1 dimension, is basically described by this ST matrix. So basically, the 1 + 1 dimensional symmetry is described by ST matrix. So that's how we describe generalized symmetry. And then the 1 + 1 dimensional gapless system is better to be described by this multi-component partition function, which is a modular covariant, and their modular transformation is given by this ST matrix of this symmetry. So combine these two give us a way to determine gapless states from the symmetry. So here we use this S3 a system with S3 symmetry as example. I'll try to explore this idea to see how far we can go. Okay, and let's see. Okay, and in the last lecture we talked about how to determine gapless states. You know, this idea not only describes gapless states, it also can be used to determine gapless state. For gapless state, the partition function is a constant. It's just a number. Do not depend on the shape of the space-time, so do not have depend on tau. And this number has to be non-negative number because it describes ground-state degeneracy for the boundary, but with a anion insertion in the bulk in the disk. So for different anion insertion on the disk, the boundary may have a different degeneracy. And this partition function for gap the boundary just describe this ground state degeneracy. Okay, and this pattern for ground degeneracy as a function of this anion insertion in the disk is also satisfy this equation. That is a kind of modular covariant. So this A is a non-negative integer now. Okay, and in last lecture we explained that if A is if this Z is non-zero, that means there's an anion condensation on the boundary because we create an anion in the bulk. Then the anti-anion must condense on the boundary, so that they have can be absorbed the boundary in order for the partition function to be constant. Okay, so therefore this non-zero A or non-zero AI means I condense on the boundary. So therefore we call this AI described so-called condensable algebra. And there's a more formal way to write this condensable algebra as a AI times the anion then direct sum. So this is but this is really categorical thinking. That is this condensable algebra basically is a direct sum of several vector space, and each anion represents the vector space, and the coefficient AI means how many copies of vector space we need to do this direct sum. And this direct sum is called composite anion, and it can be viewed as some kind of vector space. And actually, there's a multiplication vector in this vector space, so that's why it's called condensable algebra. But we did not talk about this condensable algebra. We just talked about the vector space. Okay, so this is what we covered in the last lecture. And also in the last lecture, we just gave us a concrete example how this goes. For example, we have 1 + 1 dimensional system with a Z2 symmetry. Now, usually, just Z2 symmetry just describes Z2 group. But here, instead, we use a so-called Z2 topological order or Z2 gate theory or Z2 topological, so many different names in one higher dimension to describe it. And for such topological order, they have this ST matrix is given by this form. And from the ST matrix, then we can solve this equation. So what is an integer vector such that which is a common eigenstate of ST matrix but with eigenvalue 1? We want to find the common eigenstate of ST matrix with eigenvalue 1. And also this eigenvector must have a non-negative integer entry. So we need to write a program to solve this problem. And then we find there's only these two solutions. Yeah. And these two solutions are familiar because the second entry is E. So that means E condensation. The third entry is M. So that means M condensation. So, there's two gap boundaries from E condensation, M condensation. It's just a fit, everything fit. Okay. And actually, so this kind of condensed algebra is called the Lagrangian because their condensation gave rise to gap boundary. But you can get a smaller condensation if either 1 and E, so 1 and E condense. Then if you condense 1 and E, this Z2 topological order will be completely broken, become trivial. And so that gives rise to gap boundary. If you don't condense as much, I just condense 1, so maybe no condensation, just condensing this trivial particle or no condensation. That's also corresponds to boundary. And that boundary will be the gapless boundary. Okay. And so therefore this non-maximum smaller condensed algebra is called non-Lagrangian condensed algebra. This really describes a gapless boundary. So the gapless boundary is described by this partition function, again multiple component partition function. But now it can have a tau dependence, depend on space-time shape, have a tau dependence. Okay. And we can, to construct this multi-component partition function, we can use a conformal character. There's some known function called the conformal character, and which transform nicely under SL2Z representation, and combine some conformal character with some coefficient Ni alpha bar to form a proper S3 representation. So we'll go back to this a little bit later. So then using this conformal character, we can construct this partition function. Okay. And this kind of partition function usually describes so-called non-Lagrangian condensed algebra. It's a smaller condensed algebra. But how do you see the condensed algebra? It's really this. In the conformal character, this alpha bar equal to 0 is supposed to be trivial sector. The conformal character have a trivial sector, a non-trivial sector. There's a trivial sector. So then alpha bar correspond to this trivial anions, trivial sectors. Then that correspond to the trivial boundary in a sense. And so then if basically try to say this I here means the insertion anion in the bulk anion. So basically the picture is the following. If I insert a bulk anion such that the boundary contain the trivial sector, so that means that this bulk anion somehow condensed on the boundary because it have trivial sector. However, if inserting bulk anion such that the boundary cannot have a trivial sector, then that means that anion is not condensed. So this is the more general thing than the gapped boundary. For gapped boundary, if partition function to 0 means it's not condensed, non-zero means condensed. But however, for gapless boundary, to see which anion condensed, we just examine this trivial sector or this coefficient Ni11. 1 means trivial sector. So therefore, this Ni11 is like this AI with condensing algebra we talked about before, and so that kind of determines this what condensed, what's not condensed. Yeah. So this way we can see that this particular partition function is come together with a certain pattern of condensation. certain condensable algebra. You can just read this way. From this coefficient, you can read that. Okay. And so actually so this non-Lagrangian condensable algebra also described by this non-negative integer coefficient. But however, for non-Lagrangian condensable algebra, we cannot require to satisfy this covariant condition. They no longer satisfy this covariant condition. The condition is weaker. And so actually in this paper, there's a review try to discuss this condensable algebra in general, not necessarily maximum one. And then we so then this the statement is that first is that if A is AI is non-zero, if some onion belong to condensable algebra, it must be boson. So this condition is still there. But there's some more weird condition like come with S matrix. You know, this AI times S matrix and then some ratio give rise to some kind of so-called cyclotomic integer. So there's some weird condition. And but those conditions usually come from this category theory. And so here I just translate those category theory condition into some simple mathematical statement. Okay. And so here I try to collect some condition I can collect. They are necessary, may not be sufficient. And so far so good. Actually, you can say when I try this using S3 symmetry, I will get a non-maximum condensable algebra. But since I don't get an actual one, you know, for simple case, maybe this necessary condition is enough. But certainly it's desirable to collect more conditions, determine this A completely. When A is Lagrangian, then we have some additional condition, like this condition is this A is covariant under S matrix. And there's some more inequality condition. And this condition turn out to be pretty important. If you don't have that, I think for S3, you would have actual solution. Yeah. But anyway, so those are details. Basically, I just try to say that there's some kind of machinery to calculate condensable algebra, but this machinery is not ideal, and we wish we can expand, develop this machinery further to get a more complete story. And the difficulty here is that you know, AI just describe a vector space. The algebra really comes from this product to vector give rise to third vector. So this structure constant describing this multiplication to vector is the most important. But in my calculation here, I don't even involve in that structure coefficient. So missing a lot of information. So it's kind of pleasant surprise. Even with ignoring coefficient, we can get a pretty complete story. And so here, I don't know whether one has to introduce a structure constant, or maybe in some way to really get a more complete story. But anyway, this is yeah, I just mentioned that this we still need a further development. And but what we have here already is pretty okay. That we can just go ahead and try to explore what happens. Okay. So so from here, to understand this gapless states, you can see I mentioned that if this condensable algebra is not a maximum, is a non-maximum, then the boundary must be gapless. To understand this gapless states, it's better to consider the following thing: this so-called condensation A induced topological order. Remember, this condensable algebra describes this abelian onions, which are boson with a trivial mutual statistics, means they can condense together. When you condense them, the ordinal topological order became a new topological order. If the new topological is trivial, then that's means condensable algebra is Lagrangian, is a maximum. If a topological is non-trivial, then the condensable algebra is not maximum, it's not Lagrangian. So therefore, we denote this condensation induced topological order as M/A. If M/A is non-trivial, that means It's non-Lagrangian condensed algebra. Okay. So then we say that this if M/A is non-trivial, the boundary must be gapless. So this is the statement. So that means M/A describes unbroken categorical symmetry. Remember, M describes the categorical symmetry, and M/A describes unbroken one after condensation. If unbroken categorical symmetry is non-trivial, then the state must be gapless. So this is so this corresponds to this generalized understanding of how symmetry protect gaplessness. You know, there's a lot of paper on the symmetry protect gaplessness, anomaly protect gaplessness, and there's many protected gaplessness. But I feel that all those protected gaplessness can be summarized into one statement. That is, if unbroken categorical symmetry is non-trivial, then the state must be gapless. Okay. So one way, there's one argument. You know, Michael Levin have a more rigorous proof for the Ising model. Basically, say that if a Z2 symmetry and a dual Z2 symmetry are both unbroken, then the state must be gapless. So this is a similar statement. And that statement can be translated into this: if this unbroken categorical symmetry is non-trivial, it must be gapless. The argument is following. So this three line is argument is pretty simple. So let's assume there's a boundary of this one condensed boundary of this MA is gapped. The reason we need to consider one condensed boundary is following. So we have a condensation give us this M/A. Then we have this one condensed boundary for the MA. We cannot have more condensation. If a more condensation on this boundary, then from M point of view, we will have more condensation than just a condensation. Yeah. So therefore, we have all the condensation already here give us M/A. Then the boundary between M/A to vacuum can no longer have any other additional condensation. So therefore, we consider this one condensed boundary on this part. So this is this combination can be viewed as a condensed boundary of M. Yeah. So therefore, we consider one condensed boundary of M/A. Okay. Then if this one condensed boundary is gapped, then it must satisfy this condition. Okay. Therefore, we just need to find this necessary condition. So we must have a non-negative integer vector satisfy this condition. Okay. However, this isometrics have one row, also one column, isometric symmetric, have one row describing so-called quantum dimension. So isometrics have one row with all positive with the same sign. Okay. And so therefore, with this one row with the same sign, you can show that there's no solution of this form, because this form is a one condensed boundary. Only this I equal to trivial component is a non-zero. All other equal to zero. So this will be one condensed boundary. However, if you plug this vector into this equation, then this isometrics, the first column of isometrics are quantum dimensions. When you multiply this 1, 0, 0, you get another vector given by quantum dimension, which certainly cannot be 1, 0, 0, 0. And so there's no solution of this type. So it's a very simple argument. So using the argument, we can show that this one condensed boundary must be gapless. And I think this argument is probably true even in higher dimension. You have similar ST matrix in higher dimension. You can use similar argument to show, as long as categorical symmetries there's some categorical symmetries left unbroken, it must be gapless. So I can translate that into a more Euro language. You know, so what is this unbroken categorical symmetry? Basically, there's a bunch of symmetry, But however, these bunch symmetry have non-trivial statistics between them. So usually when we say symmetries, then the symmetry means that all these symmetry charge have a trivial mutual statistics between them. So therefore, unbroken symmetry do not guarantee gaplessness. However, when I say unbroken categorical symmetry, this categorization involving both symmetry and dual symmetry, and the symmetry dual symmetry always have a non-trivial mutual statistics between them. So the using more traditional language is that when we say there's unbroken categorical symmetry, it really means that we have an unbroken symmetry with non-trivial mutual statistics between them, then that's guaranteed gaplessness. And but the non-trivial mutual statistics between symmetries can be referred to as an anomaly. And so basically, so that becomes Euro statement: anomalous symmetry guarantee gaplessness. But sometimes non-trivial mutual statistics goes beyond the anomaly. The anomaly don't capture all that. So it's more convenient to say we have a symmetry with non-trivial mutual statistics. That's a more general way to capture this actual feature of symmetry, and that's guaranteed gapless. And then in the more formal language, that means you have a categorical symmetry which is left unbroken. Whenever you have unbroken categorical symmetry, the state must be gapless. Okay, and actually in Liang Kong and Hao Zheng's paper, there's some earlier paper, yeah, they didn't mention categorical symmetry, but however they mentioned this topological weak rotation. And basically they say you have topological order and this like Grant's wave function. Then you just weak rotate them, make a Grant's wave function stick in time direction. Somehow that represents a gapless edge. I don't know whether there's a proof for this, but I really like this picture. It's really that it's really saying that if you know the Grant's wave function have non-trivial topological order, there's a canonical boundary. Just rotate the wave function into time direction, you should get this canonical gapless boundary. And at the moment maybe it's at the moment it's kind of wishful thinking, and we still don't know exactly how to do it. But I feel pretty strongly this picture works, but we don't know how to make the very concrete. I don't know whether some kind of tensor network, something like you can make it very concrete. Just rotate this tensor network, you just get gapless states. Yeah, that seems very possible. Yeah. So therefore, this topological weak rotation and this one condensed boundary is basically the same thing. Basically, we say that one condensed boundary is some canonical boundary, which is a gapless. And okay, so this is I think they have this topological weak rotation motivated from mathematical consideration, which I do not understand. So I couldn't reproduce their argument, but I do believe the result they have. Okay. So with this picture, now we have this Lagrangian condensed algebra which describe a gap state. We also have the non-Lagrangian condensed algebra describe a gapless state. So therefore, the general picture will be this. We have this. We can using this unbroken categorical symmetry, like this A1 plus M is condensed algebra. Sorry, and this also condensed algebra. We can use the condensed algebra to label different states. Okay, and this label includes both gapped and gapless states. So this is maybe the wonderful main message from this consideration. Before the feeling is falling, before when we have a symmetry, we ask what is a gapless state or gap state with the symmetry, including broken state, unbroken state, all other states. And it sounds like this question is too general, and immediately you can say there's infinite number of possibilities. So this question don't have much content. But here I try to say that Well, if you know the condensed algebra, maybe you can label all the gapless state with using condensed algebra. This way of looking at all these gapless states may be sensible and can give you a way to understand all these gapless states. But certainly there's an issue that maybe for each condensed algebra correspond to the there may be many different boundary states. Still infinite number of boundary states correspond to that, and so it's still not determined. But on the other hand, I try to say there's a so-called minimal one. For each condensed algebra, there's a minimum boundary state, and this minimum boundary state may be unique, or maybe almost unique, something like that. So this is a kind of a picture we have to use. And there's another thing which is very suggestive from this picture is that you can see this M condensation give you this so-called Z2 symmetric states for Ising model. E condensation give you Z2 symmetry breaking states. And this no condensation happen to be transition between these two. So therefore, these two Lagrangian condensed algebra give rise to gap states. However, these two Lagrangian condensed algebra have a common subalgebra, which is A equal to 1, their common subalgebra, which describe a gapless states. So it's very suggestive that if A1 and A2 describe two gap states, the transition between A1 and A2 is given by the gapless states, and these gapless states are described by condensed algebra, which is subalgebra for both A1 and A2. So again, these examples fit that picture. So maybe so this may be also a general thing, general statement. So you can use in condensed algebra and their subalgebra subalgebra structure, try to guess what kind of phase diagram it may be. Okay. So here is I just maybe just mention how do you obtain this modular covariant partition function? Okay. And the modular covariant partition function would satisfy these two conditions. And yes, go on. Yeah, sure.
So when you have this kind of transition between two condensable algebras,
yes,
described by the subalgebra, does that mean the transition for the second order continue?
Okay, yeah. Yes, thank you for the question. Yeah, I'm kind of too quick here. Certainly, transition can always be first order. Okay, and then when the first order transition, then there's no gapless state at transition. Here we assume, suppose we fine tune some parameter to find some continuous transition. Then you ask what is its CFT at the critical point? So this conformal filter at the critical point actually describe this a common subalgebra. Okay, and this really means that we have these two transition, two gap phase like this, and we first assume there's always a way to tune to some critical point. Means the continuous transition can be multi-critical point. And so this may be a statement, probably is true. But okay, yeah. Thank you for the question. Because for any condensable algebra contain identity, contain trivial onion. So any pair of condensable algebra contain at least this one. So that seems to suggest that we can always fine tune a parameter to obtain a continuous transition, multi-critical one, described by this condensed algebra. So actually, that's one conclusion, as a suggestion from this picture. So that's a statement usually between any two gap phase, there is a continuous transition if you are willing to fine tune enough parameter. But here it claims that you fine tune finite number of parameter, not infinite number of parameter. You can get there. Okay. And how many parameters to tune determined by this kind of gapless states. So this one condensation gives you some gapless states, their CFT. Then you need to count how many relevant operators in this CFT. Then tell you how many parameters you need to tune to get this transition. So this this statement is So let's go back to the Landau theory. You know, when I first learned Landau theory, I say if two phases have a group subgroup structure, we say there's a continuous transition. But there, I kind of assume the continuous transition is stable, means there's a continuous transition by fine-tuning only one parameter. Then realize that this statement is not true. Because if other parameters contain quartic or cubic term, then in general, there's no continuous transition. You have to fine-tune more. So therefore, now we say that, so we say we have to be careful. We should not put words in Landau's mouth. So maybe Landau's theory really say that if two symmetry breaking states have a group subgroup structure, there is a continuous transition, but could be multi-critical point. If fine-tune enough parameter, there could be continuous transition. Okay, so this became Landau's theory. Group subgroup structure allow that. And now with this quantum theory, then we say between any two, there is a continuous transition. We don't need any of this group subgroup structure. In any two gap phase, there is continuous transition if you're willing to fine-tune enough parameter. Yeah. So that's a suggestion from this. Yeah, thank you for this credit. I should really expand on this. Yeah. And so the picture is quite different from Landau's picture. But on the other hand, we're also using Landau's the blueprint. You know, we're still using the same language, same words. Just that the content is a little modified. The concept, the framework is still the same. But the content is just modified a little bit. Yeah. Okay. So from here you can see that we already described if this condensed algebra is a Lagrangian, then how to obtain this the gap, the boundary by solving this modular covariant equation. But however, for gapless boundary, then how to find this partition function satisfy this equation? I will mention this is very difficult, and almost looks impossible because this algebraic equation you cannot determine the function from algebraic equation. And then I also mentioned that actually this problem probably doable. I don't have proof, but I think it may be doable in the sense this partition function you expand as a polynomial of e to the I 2 pi tau. Actually, this z is almost like a polynomial of e to the I 2 pi tau, also called q, polynomial of q. This polynomial have a non-negative integer coefficient. It's a very, very special polynomial. Then we have this very, very special polynomial, then this algebraic equation probably can indeed determine this function. And we don't have a way to do so. We don't have a formalism or algorithm to do this. That's a really very important open question. And the same thing also true in higher dimension. We can solve in higher dimension, we basically can solve the higher dimensional gapless system. Okay. But however, in 1+ dimension, there's a hacker's way or guessing way to do it. Because the mathematician, there's a lot of development in conformal field theory. They develop so-called conformal character. Those conformal character are Hallamov function for q tau, such that they are polynomial of q with a non-negative integer coefficient. So this conformal character is people construct this conformal character, many of them. And we have a library of conformal character which is a polynomial of q with a non-negative integer coefficient. So therefore, using this library of conformal character, we just put the two characters together and finding some non-negative integer coefficient. And so that therefore, so this construction is guaranteed to have a polynomial with non-negative integer coefficient. And then because each conformal character is a SL2Z representation, we just combine two SL2Z representation so that they became another SL2Z representation given by this ST matrix, such with this condition. So this is really the guessing way. And but here is basically computer search and also some human intuition. You need to guess which two conformal character you want to try here. Then there's a program to find out this coefficient. And most time we find that there's no solution, there's no desired solution. Then you just try another one. So then you do need some intuition. You need to know which one is the right thing to choose. Then so at least you have a non-trivial solution for this. But at the moment, this is all we have, and it's actually it's already pretty useful. I do not want to say powerful, but it's pretty useful. Okay. So so in the following, we'll just describing this approach. But however, there's another factor which is important. So this coefficient, actually, this coefficient is again non-negative integer coefficient. This non-negative integer coefficient is very much like a we have. Remember, AI is condensable algebra. AI satisfies some condition, and but this coefficient with this rank 3 tensor is much almost like AI. And in the way you can do the following, not folding, we can do the following thing. You know, this condition is this condition gave rise to the condition on this rank 3 tensor. We can view rank 3 tensor as a rank 1 vector. Just flatten all the 3 index. And when you do that, that condition can be viewed as this one. Now n is viewed as a rank 1 vector. But now the S matrix became the S matrix for topological order tensor with the S matrix of a right moving conformal field theory and the one with a left moving conformal field theory. The tensor product of 3 S matrix and tensor product of 3 T matrix. And this ST matrix for conformal field theory is known, is given by the conformal character. For every conformal character, there is a ST matrix for that conformal character. And so basically we can do this so that you can become this equation. And this equation almost like finding gapless boundary of topological order formed by these 3 S matrix, the stacking of 3 topological order. Yeah. So usually the conformal character indeed have a corresponding topological order, bulk topological order. So basically we kind of solving this equation. So therefore solving this once you know the conformal character, solving this rank 3 tensor is the same thing as solving the gapless boundary, but of this composite topological order. Yeah. And this observation is important. Remember that because those condition is only necessary, we have a more condition on A. There's in addition to this, there's a more condition. So when you have this point of view, this n vector should also satisfy this additional condition. So we have so not only have this condition, there's some additional condition on this n vector. Yeah. So this is kind of important to know. Okay. So therefore we can find this solution. Usually we may find many solutions, even for the given symmetry. ST matrix, given symmetry, there could be many solutions. And but those different solutions usually have a different central charge, means a different gapless excitation. And usually we think the one with a minimal central charge, with a minimal gapless excitation, are most stable. So we want to get this most stable one. And so this looks like yeah, it's not so good because we want to use this condition to determine gapless state, and you end up you not determine it. But actually the situation is not so bad. And for example, when we say that this Z2 symmetry breaking transition have a gapless critical point. And we say this gapless critical point is central charge 1/2 of CFT. But that statement is wrong. We only say you have a symmetry breaking transition point. That gapless point, gapless state at the transition point may not be C to 1/2 of I think CFT. Maybe many other things. Actually, this is infinite number of choice because you can stack with any gapless state there. And that could be the possible gapless state at transition point. So when we say a particular CFT describing symmetry breaking transition, we already implicitly assume we are talking about the minimal CFT, minimal one. So here we are doing the same thing here. So what I try to say is that this ambiguity here is not worse than the Euro statement. We feel pretty sure the transition of Z2 symmetry breaking transition is Ising CFT, but that statement actually have ambiguities, and here we have similar ambiguities. Yeah. Maybe in the end we'll talk about this ambiguity. We'll go back to this ambiguity again. So that is so that is a question. So now let's consider this Z2 symmetry transition. So you go back to this Z2 example. We have 4x4 matrix. Okay. And using this 2 4x4 matrix, and yeah, then we try to solve in this equation, and using this guessing method to see what result we get. And the one result is just this. So here we have Z2 symmetry. We naturally guess using Ising CFT character to construct it. Then we find this n integer rank-3 tensor gave rise to this kind of a 4-component partition function. Okay. Again, let me try to look at it. You can see this 0 means this conformal character of Ising CFT are labeled by so-called primary field. The index here is a dimension, scaling dimension primary field. Scaling dimension 0 means identity operator. 1/2 is a fermion per psi, and 1/16 is a sigma. This is a primary field. Okay. And so you can see that this again, you can see that this chi0 square only appear at this one component. So that means we only have this one condensed. So this is one condensed. If chi0 component also appear in the second component, that will be the gapless boundary, but for the 1 plus e condensed boundary, not the one condensed boundary. Okay. Usually when that happens, some other component must be 0, you know. And here we only have one condensed boundary, the other component all non-zero, you know. Yeah, if chi0 square appear in other component, some other component should be 0. That's usually the pattern. Okay. So we'll see the pattern which nothing is 0 and the 0 square is appear in one component. That corresponds to one condensed boundary. And there's another one condensed boundary. Using this, this is a 4-3 minimum model, and there's a so-called 5-4 minimum model. Central charge is not 1/2, it's 7/10, I think. Yeah, and we have another boundary. It's the same ST matrix, same 4x4 matrix. So this just transform in the same way. Okay. Again, this is the one condensed boundary. Again, this 0 appear in the one component, and nothing else is 0. So this is but from here we see that this point is have a higher central charge, is more unstable. Okay, and also this one have a central charge 1/2 for right mover, and so it's more stable. So this is what you have. Let me try to using this. I think I should use the presentation mode. Okay. So so then how you see the relevant operator, you know, actually finding this solution, we can even know relevant operator, and it's very easy to see. First, the relevant operator means the total scaling dimension less than 2 be relevant. Here I say a conformal character would have this scaling dimension here. So like here the scaling dimension is 1/8, because we have right mover, left mover have a square, so it's 1/8. So therefore this operator is a relevant operator. Oh. Yeah, this operator is a relevant operator. Okay. However, this relevant operator are in the E sector. E sector is a Z2 charge. So actually this operator, this dimension 1/8 operator carry non-zero Z2 charge. So if you add this to the Lagrangian, this operator creates Z2 charge. So breaks Z2 symmetry. So therefore, the symmetric operator all in this zero component. And here, there's a, let me see. This is a 1/2. Yeah, there's a one relevant operator. Yeah, this is relevant operator. Yeah, there's a one relevant operator. So therefore, there's only one relevant symmetric operator. Means that to get this critical point, we need to fine tune one parameter, which is temperature. So because you have this relevant operator, this gapless state is not the phase, but it's a stable continuous transition. Okay. And here you can see that 1/10 equals 1/5, schematic 1/5. This is relevant and symmetric relevant. And this one is 8/5, also symmetric relevant. So therefore, these two, this critical point with a higher center charge have a two relevant direction. Means that we need to fine tune two parameters to reach this critical point. So this one is a tri-critical icing. Actually, it's also the critical point break Z2 symmetry, but we reach that by tuning two parameters. So this is example just demonstrate once you get a solution, we can read a lot of information. Yeah. Okay.
Does this list go on like?
Yeah, there's more. Yeah.
Is it like all minimal models, but it makes a jump every time? Or? Is it like all like even minimal models? Like so
no, no, not this. I think for the minimal model, there's only two model with the same solution.
Right.
Other solution will be C equal to 1 or higher than 1. That'll be more wild, actually. It's a much less control. And there are more solutions. Okay.
But how about this Yang model? Non-invertible.
No, here we're looking for unitary model. Yeah. And actually, that's very important. And I think for non-unitary model means that this particular function is polynomial with the integer coefficient, but you remove the non-negative condition. I think that's the case. Yeah, I'm not totally sure, but I imagine that's the case. So therefore, there will be more solutions, and that will be the non-unitary solution. So actually, if you suspect some non-unitary CFT should be physical, should be there, this approach also works. It just remove one condition. Is you allow you're only looking for integer polynomial, not a non-negative integer polynomial. Then you have more solution, and also that would be kind of interesting. Yeah.
So here is it possible to show that the icing is minimal?
What?
You mentioned that for condensing like this one.
Yeah.
Should be a minimal.
Yeah, the icing is this a minimal one. Yeah, this as a minimal one condenser boundary. The icing is a minimum one boundary, but it's a 5-4 minimal model. It's not minimal one condenser boundary.
So my question is there a way to show that the icing is actually?
Yes, because 1/2 is the smallest. So there's no smaller one. But actually, I should say I should be careful. Okay. Okay. Again, thank you for the question. There's two definitions of minimal. So I using central charge to define minimal. You know, in that case, I think it's a minimal, and I can show that because that's 1/2 is a minimal. There's nothing smaller than 1/2. But however, a more physical way, actually using central charge to define minimal is not proper. A more proper way is using the relevant operator. So I think have a one relevant operator, symmetric relevant operator. This tri-critical I think have two symmetric relevant operator. So in that sense, I think the minimal. But however, I cannot show that maybe there's a even higher central charge CFT with only one relevant symmetric operator. That may happen. And actually, if that happens, that will be physically very relevant. That means the Z2 symmetry breaking can have another stable transition. described by the higher center charge fixed point, not icing one. And that one also have only one relevant operator, then just fine-tune one parameter can go through that. And this can happen, I think. There's some paper say between same two phase, you may have different CFT. So this is the way this can happen. And so even for Z2 center breaking, it's worthwhile to study the other solution to see whether there's other solution with only one minimal or one relevant operator. But to get other solutions is difficult because other solution for minimal model, I think there's only two solutions. For other solutions necessarily involving the central charge one or higher than one solution. And those models are more wild and we have less control. And so we need a more better algorithm to handle that. But finding other solutions, and especially other solution with only one relevant operator is very significant. Yeah.
But using like solving the equation, you can just bound in this case that the center charge is.
No, we already have one half solution. There cannot be half solution with a less than less than one half. One half already minimal. But for other model, yeah, you
like from solving these equations, you get about minimal, the smallest interval.
I think maybe yes, but there's a lot of so-called modular bootstrap, and the modular bootstrap not using the guessing approach, using the more general approach. But my understanding is the modular bootstrap that people only use a non-negative condition, not using the integer condition on this polynomial coefficient. And but you only using non-negative condition, one can already put a lot of bound. I forgot whether it's a bound on central charge or not, but also there's a bound on the operator with a minimal scaling dimension, or maybe with a charge operator with scaling dimension, something like that. So one can do things. Yeah, one can get a more general bound, not using guessing. Yeah. Yeah, again, I'm kind of selling. Yeah, I feel the modular bootstrap, especially using this modular covariant partition function, could be a promising approach. Maybe simple because you don't need to know the descendant field, all this operator coefficient of descendant field, which I feel very confused. But this may be simpler. And also we have Z2 cross Z2 symmetry, and there's more condensed algebra. And here I just want to say that in this case, you have you may have SPT states. Yeah, sorry. In this case, you may have SPT states. And so let's describe this a little bit. We have Z2 cross Z2 symmetry. Then you have this. You have two symmetry, Z2A, Z2B, for example. Then in the bulk, you have a EA and MA, EB and MB. That's a kind of anion in the bulk. If E do not condense, we can use M to construct condensed algebra, construct the maximum condensed algebra. This is a Lagrangian condensed algebra. Then you can see only M condense. So the dual symmetry is broken, but the symmetry is not broken. So this gap boundary describes a fully symmetric boundary. Okay. And this one, we have another condensed algebra, just all E condensed. The E condensed means a break symmetry, but do not break a dual symmetry. So this boundary is a total broken boundary. Okay. Yeah. Then we have this. This one is we never condense M. Okay. So this is another boundary. We condense those combinations, but there is no E condensation, no B condensation. Means symmetry is not broken. But also, it's not symmetric state like this. You know, symmetry means the MA and B condense, but this is not. So this other one actually is a SPT states. And this one, EA-EB, they break this combination. So this combination of Z2 charge is broken. So this is diagonal Z2 symmetric, another diagonals are broken, something like that. So this is Yeah, this is just to demonstrate that by studying condensed algebra, we not only get the symmetric phase and the symmetry broken phase, and also SPD state are there. So computing condensed algebra corresponds to computing all the gap phase. In higher dimension, this should be also give rise to computing possible topological orders. But the computing condensed algebra in higher dimension may not be easy. Probably easier to compute the topological directly. So I don't know whether there's any save anything or not. But this at least this is another understanding. Okay. And so maybe let me just skipping this part. And okay. So let's go back to the S3 symmetry we talked about. So now we have a more non-trivial symmetry, S3 symmetry. For the S3 symmetry, and their categorical symmetry is a S3 gig theory in one higher dimension. Okay. But here, usually I think the name of S3 gig theory may the meaning may change, because in old times when we say S3 gauge theory means we don't have gauge flux, only flux fluctuation, no matter, so mean no gauge charge. But here the S3 gauge theory means with both flux fluctuation and the charge fluctuation. So in a sense, so S3 gauge theory with the charge fluctuation is called this topological order. This S3 topological order. So the topological just means you have a charge excitation. Okay. So the charge excitation in S3 gauge theory is given by the S3 representation. The one means a trivial representation, just nothing. A1 is a one-dimensional representation. A2 is a two-dimensional representation. Both are irreducible. S3 only have these two irreducible representation, and that is a two charge particle. Okay, and there's also S3 also have flux. I mean, if you go around a flux, then you get this S3 gauge transformation. The group element. You go around the flux, you get the group element. And but however, the only contrast class of group element give you correspond to the gauge invariant flux. Okay, so B is a one flux correspond to one of flux correspond to this contrast class with a two group element. And the C is another contrast class correspond to contrast class with a three group element. So that describes the flux, the non-abelian flux. Then there's a B1, B2, and the C1 is a bound state of this charge and the flux, some flux charge bound states. So the total is 8 anions in S3 gauge theory. And they have this fusion rule. It's pretty complicated. So for S3 gauge theory, already get a pretty complicated so-called modular tensor category. So some category language will be very useful for this. Okay. And also at least this pair, this 1, it means the quantum dimension is 1. The next number 0 means topological spin 0 means boson. So this topological spin is 1/3. It's actually an anion. But quantum dimension 2 is a non-abelian anion. So this is a non-abelian anion here. Okay. So so there's a 10 condensed algebra. Here I say potential means we obtain this 10. No, there's 10. Maybe 8. I counted wrong. Oh, sorry, 8, not 10. We have 8 condensed algebra. We say the potential because this is obtained by necessary condition. So there could be fake one, you know. And but for this simple case, I think they are all real. They are not fake. Okay. And the top of 4 is this Lagrangian condensed algebra. This bigger one. And then you can see that this like this one, 1BC, this is the flux condensation, no charge condensation. This corresponds to symmetric state. So this is the S3 symmetric phase, total symmetry. And this one, A1, A2, there's a 2 here. this is unusual. It's hard to guess why we have need 2 here. But from the calculation, yeah, we need 2. In our understanding, we just say we have the first charge condense and the second charge condense. You break all the symmetry, you get 0 phase. But mathematically, there's a 2 here. It's pretty important. So anyway, this condensed algebra condensing all the charge is a Higgs phase. So it's a 0 phase. There's no symmetry. Okay. Then this one, you're condensing A1, so they break the Z2, so it have Z3 symmetric phase. Here, A2 becomes Z2 symmetric phase. So there's all four symmetry breaking partners here. There is no SPT phase because there's no additional Lagrange condensed algebra. So S3 indeed has no SPT phase. Okay. So therefore, we put these 4 condensable algebra in a corner. Okay. Then try to see what kind of phase diagram we could have. Yeah. So from here we see that this let's do the simple one, like this pair. Okay. This pair have Z2 symmetric phase and the Z1 symmetry phase. Okay. So we expect this is just Z2 symmetry breaking, just Ising model. Okay. So then we look at these 2 condensed algebra. And their common condensed algebra is a 1 plus A2. That's a common part. Here is only 1 A2, here's 2 A2. So this is subspace, so it's a sub-algebra. Okay. So if you condense 1 plus A2, so this is not a maximum condensed algebra. This is one of a non-Lagrangian condensed algebra. Is this one? Okay. If you condense this algebra, what happened to this S3 gauge theory? Again, you do some calculation. It turns out that condensing this kind of anion gives you Z2 gauge theory. Yeah. So again, this calculation can be done. Okay. So therefore, the categorical symmetry describing this transition is a Z2 gauge theory in one higher dimension, which is and one condensed boundary of this Z2 gauge theory is this Ising critical point we just studied. So this is a way to see why this pair of condensed algebra have a transition given by this certain CFT. So that's how we do this. Okay, and for the for this Z3, okay. And for the Z3, Z3 to Z1, it's just ordinary this Z3 symmetry breaking. And indeed, we find this their common condensed algebra is 1 plus A1. If you condense that, this Z3 gauge theory will become S3 gauge theory will become Z3 gauge theory again, as expected. So this thing works pretty well. Okay, and then between S3 and Z2, this became kind of tricky. Yeah, S3 and Z2 is tricky because there's no condensed algebra here. There's a missing one. Yeah, there's a missing one. So if you look at this, the common algebra should be 1 plus C. So 1 plus C should be here. It's the describing transition. But 1 plus C is not a condensed algebra. Do not satisfy this condition. So this is a surprise. Yeah, 1 plus C is not condensed algebra. Okay, so therefore S3 to Z2 transition has to go through this, has to go through 1. So the critical point is a 1 condensed boundary of S3 gauge theory. This is a weird. Okay. Similarly, this S3 to Z1 transition, from here to here, also 1 condensed boundary. So actually, 1 condensed boundary can describe any of this transition, including this. Okay. So things became very puzzling. So you kind of stuck here. It's what's going on? Is this picture suggests that for S3 to Z2 transition and S3 to Z1 transition are described by same CFT. But maybe this too much because we say that there's multiple one condensed boundary. So one condensed boundary corresponds to several CFT. So one level one condensed CFT describes S3 to Z2, another one describes S3 to Z1. So maybe there's some additional physics we should think about to fix this issue. But at least this point of view raises questions. And so we can think in this way and try to making some progress. Okay. So this is kind of a picture and the puzzle we get. So what is CFT between those phase transition? And really, this S3 to Z3 is a 1 plus B, and that's a condensation give you Z2 gates here. So this one also I think CFT. So everything else is clear, but it's just these two seems not so clear. Yeah.
Is it somehow related to like Z2 is not a normal subgroup?
Yeah, this I think relate to that. Yeah. If S3 is just Z2 times Z3, I think we will have this one. Yeah, but this is not normal. There's some twist here. So this non-abelian thing is have non-trivial effect here. Okay. So let's try to do it. And so basically we need to find this. We need to find all these this non-maximal or non-Lagrangian condensed algebra. What is the corresponding gapless states by solving this equation? Okay. Okay, for one condensed boundary of S3. So basically, we're talking about talking this one, just a one condensed boundary. And again, there's a yeah, we have a solution. There's an 8 component. There's 8 component partition function because the bulk S3 gates here have 8 onions. So the partition function would have 8 component. And here again, there's intuition here. This 6-5 minor model somehow is compatible with S3, and we just plug in, we get this. So then we can try this 4-3-5-4. There's no one condensed solution. Actually, there's other solution, but not one condensed solution. But this one condensed solution only appear in 6-5 first. And so we get this one. And this one I have to read this because this is one condensed because the 0, the chi0 square only appears one sector. And this is the only operator, symmetric operator. Symmetric relevant operator. This is the only symmetric relevant operator. These two operators are not relevant. So this boundary is pretty stable, only one relevant operator, and the central charge is pretty low. And then there's another one condensed boundary. Yeah, there's another condensed boundary. Which I move this away a little bit. Another condensed boundary comes from this so-called 7-6 minor model. It's the model with higher central charge, so more heat capacity here. Okay, and then there are two operators with a low scaling dimension. So so this is a multi-critical point. Yeah. It turns out that it turns out that let me see. Do I say that? No, I didn't say that. Okay. It turns out that this first critical point is describing this S3 to Z2 transition. So there's this transition just pulse model, the 3-state pulse model. People study that, simulate that, and then the CFT they find match this scaling dimension. The central charge match this. So therefore the pulse 3-state pulse model from S3 to Z2 symmetry breaking are described by this one condensed boundary and described by this particular one. Okay. And so the question is that what about the S3 to Z1 transition? Yeah, this is we don't know. This question is still open. And seems the numerical calculation suggests that it's not this, not pulse model, not this one, and not even this one. And actually, there's some puzzle here. If it is this one, that means S3 to Z1 transition is a multi-critical, cannot be a stable continuous transition. we did some preliminary numerical calculation. Seems also not this one. This one has center charge for right mover is a 5/6. The one seems is a 1.3, seems something 1.3, but we are not so sure at the moment. Yeah. Okay, so therefore this yeah. So we have a trouble to determine this S3 to Z1 transition. So what is but we say it must be one of one condensed boundary, but which one? And we are not so sure. So this is still an open question here. Okay, then for other boundary and okay, yeah. So here I took the 1 + A condensed boundary. Okay. And this boundary is a CFT is a 5/4, you know, and so you can see the pattern. There are two the chi0 square appear in one and A component, these two component. So this is a non-trivial condensation. And now because these two condensation and this some anion is confined, so there's a 0 here. So this always appear together. And this one we use this I think this one is a 5/4. It's a 5/4 minor model can fit this 6/5. No, 6/5 or 5/4. Oh yeah, 6/5. So 6/5 minor model describing this transition. Okay. Okay, what that means is the following. Okay. This transition from S3 to Z2 transition is described by 6/5 minor model. But Z3 to Z1 also described by 6/5 minor model. So describe same 6/5 minor model. So it's very similar. But however, the pattern is different. You know, for this S3 to Z2 transition, the full partition function is this one. So the Howard symmetry, there are 6/5 minor model, but the symmetry sector, the charge sector, the scaling dimension are different. You can see in the total symmetric sector, we have this kind of scaling dimension appears. Okay. And in the A1 representation, we have this kind of scaling dimension. And but for this, you can see in the 0 A1, the pattern scaling dimension is the same, you know. So although they both describe a 6/5 minor model, but it's a somewhat different CFT because the combination is different. Yeah, so this is just an example that it's the same 6/5 minor model, but different combination, strictly speaking, the different CFT. You can also see this feature here. Yeah. And so they can skip this. Yeah, those are just a similar thing. So at the end we get this. So we do numerics, and then we see that yeah, we have S3 to Z1 transition. Okay. And as I mentioned, the numerics is not completely sure, and we kind of flip-flop about whether this transition is lines first order or second order. And currently, I think this is second order. And but this is really line here. So it means there is a stable transition. It's a stable transition means so either it must be this one, but center charge doesn't fit. Center charge is higher. Okay, and it cannot be this one. This one have two relevant direction. So this suggests that there's another CFT with a one condensed boundary of S3 symmetry with only one relevant direction, but a much higher center charge. Center charge is higher than 1. Yeah, this is again, this is something interesting. And do we have such a CFT? Yeah, and if you have some CFT, then maybe this correspond to this transition. Okay, so that is a story. Okay, and then there's another model. Okay, yeah, there's another model. Let me see. Do I have a third model? Yeah. Okay. There's another model. It's a by fine-tuning. Then we have this. There's a multi-critical point. Okay. And this multi-critical is kind of stable. Means there's two relevant directions between S3 to Z1 and Z2 to Z3. Yeah. So looks like it's very tempting to this again. This multi-critical point also one condensed boundary. Okay. It's very tempting to assign this one, this 7, 6 CFT to this multi-critical point only two relevant direction. But again, we're not sure. The sun charge here is pretty low, and so the things that you can see, if this transition have sun charge bigger than 1, then when this transition shrink to a point for this to become multi-critical point, then sun charge should be even higher. That's the convention. So if this is a multi-critical point, sometimes maybe you should be even higher than 1. So you can see here a lot of confusion but in some sense I want to say that I'm glad we have confusion, because before we don't even have a confusion. But this confusion is very concrete. We have some choice, and some confusion, and then there's certainly clearly some moment problem to solve. Okay. Yeah. So this either is this one or sun charge bigger than 1. And yeah, this one, I don't know. Yeah. So can we say anything more definite? Okay. And this maybe this is another application which is I think it's the easiest thing to do at this stage. If you look at these 8 onions, we notice that A2 and B are very similar. They both have a quantity dimension 2, both are bosons. Actually, if you look at this fusion matrix, this is fusion rule Nijk. You can see that actually the fusion is a invariant under exchange of A2 and B. Yeah. So that means that this S3 gate theory have automorphism of changing the second charge and the first flux. Exchanging 2 is automorphism. Okay. And so under such automorphism and changing A2 and B, let's see what happens. If changing A2 and B, we can see that S3 go to Z2, Z2 go to S3. And similarly, this A2 to B, and these two. So basically, changing this automorphism means this reflection about this vertical line here. You just flip. So therefore, this phase diagram is controlled by this categorical symmetry, have this automorphism flipping vertical line. This means the S3 to Z1 transition and the Z2 to Z3 transition are the same transition, at least are dual. Means if you have a model that we have a continuous S3 to Z1 transition, then we must have another model, a dual model, which have a continuous Z3 to Z2 transition, described by same CFT. Yeah. And this is this is something more concrete you can say that by studying the automorphism, this self-duality of this categorical symmetry, we can map phase into each other and make statement of phase transition. Certain phase transition are identical or related. If you believe there's a continuous S3 to Z1 transition, then there must be continuous Z2 to Z3 transition, which is surprising from Landau theory point of view. Yeah, but from this point of view, it's more natural. So from here you can see that, as I mentioned, or to emphasize that Landau theory say that continuous transition happen between group subgroup. But however, the more quantum theory say that the continuous transition can happen between any two gap phase. And but however, this the quantum point of view or this categorical point of view also tell us sometimes the transition between gap phase are related. And this can be seen from this categorical symmetry. Yes.
Yeah, I don't know how to ask my question in this example, so I'll ask in this symmetry example.
Yes.
So for the Ising model, you label the critical point by D2 gauge theory. That'll be the categorical.
Yeah.
But if I'm exactly at the critical point, I also have this Cameron-Bonnier symmetry. So I have this
Exactly.
Symmetry. So then the gauge theory one I mentioned would be this like twisted D2 gauge theory.
Yeah.
So why do you label the critical point by D2 gauge theory and not by twisted D2 gauge theory?
Yeah. But we should do both. So this is maybe the yeah, since you raised question, so let me just go here. Yeah, maybe let's do this way. Okay. So what is the picture? This picture really says that so this we have quantum field theory like a CFT. So like this Ising critical point. This gapless states some CFT. Okay. So usually when you have a CFT, we have this modular invariant partition function. We have the modular invariant partition function to look at CFT means that we ignore symmetry. We don't look at the symmetry. Okay. And one way to expose the symmetry is to view this modular invariant partition function viewing this CFT as a stacking of this picture. And we have a topological order in the bulk. And there's an anomalous multi-component partition function on the boundary, and another constant partition function another boundary, this is a gas boundary. Then this modular invariant partition function is given by this formula. This zi r tilde is a constant. This is a constant partition function, just some 1 or 2 some numbers. And this multi-component partition function is like an inner product between the two. Then you get a modular invariant partition function. But however, this decomposition of this looking into this way, we call this a decomposition. This decomposition exposes the symmetry. So therefore, for the Ising CFT modular invariant partition function, we can expose a symmetry like this, where M is a Z2 gauge theory. It turns out that for the same Ising CFT, we can expose more symmetry by choosing this kind of decomposition, where M prime is a sort of double Ising model, where we gauge the EM exchange symmetry in the Z2 gauge theory, we get double Ising model. And so therefore, this same modular invariant partition function can have 2 decomposition, but one of them exposes more symmetry. So this is notion for maximum categorical symmetry. Okay. So the hope is that this maximum categorical symmetry may give rise to this one-to-one correspondence. Yeah. So when I have a gapless states, we want to search for this maximum symmetry. When we find the maximum symmetry, then maybe the symmetry and the gapless have a more correspondence, more direct correspondence. For the Ising model, the example is that the double Ising model is their maximum categorical symmetry. Yeah. This part is really kind of open, and saying the one-to-one is I don't know, I'm not sure it's really true, but I'm hoping it's a few to one at least. I mean, the one with the maximum categorization may not be unique, but also maybe not too many. It's just a few, then we can use another physical argument to pick which one, and something like that. Yeah. So this is a kind of a picture. Yeah.
So then in the S3 example, maybe the critical point isn't labeled by S3 gauge theory, but there's a larger.
Yeah, that's for sure. Yeah. So all those critical points have the S3 gauge theory is not the maximum. Okay. All these critical points they are not maximum. There's an additional maximum one. Okay. Yeah. And so here I just want to say. Actually, yeah, I should update this. Okay. Anyway, so I just want to say the following. We can, even for anomalous symmetry, when the symmetry have anomaly, then the bulk topological is no longer S3 gauge theory, but S3 Dagger-Witten model. Yeah. And so then the Condensable algebra will be different. And for example, we have this. So you know for S3 symmetry, the anomaly is a Z6 anomaly. So there's a first anomaly, second anomaly, and a third anomaly. And the fourth, 5, 6 are related to these previous 3 by charge conjugation, complex conjugation. For the first kind of anomaly, you can see that we only have one Lagrangian condensed algebra, which have a gap phase. And there's only 2 non-maximum or 3 non-maximum one. So we can get the gapless states. And this is not updated, but this one is known now. I forgot. It's some very complicated conformal theory. Yeah. So all these, and this one, something like that. So this one, for second anomaly, this is a conformal field theory. It's like a SO9 level 2 conformal theory. That's for the left mover. For right mover is E8 level 1. So this combination, so central charge is 8. It's very high central charge. But I don't know whether it's a minimum one. Maybe there's a one with a smaller central charge, but we couldn't find the minimum one. But even for such a high central charge, it's kind of interesting. This CFT have no relevant operator. So this is phase. So it really says that when you have a 1 plus 1 dimension, the S2 anomalous symmetry, the second anomaly, and there's a gapless phase with no relevant operator. Yeah, and this is actually this one is a stable gapless phase. And we also have these 2, this one and the third one. Actually, there's one. I forgot to update my slide, and so I think this case there's a more relevant operator. They are not the phase. Yeah. So at least one can get something from all this approach, but also certainly there's a lot of open questions. Yeah, and yeah, so we already covered this part, and yeah, so this part really try to say that you know, when you consider boundary of topological order, we're really talking about anomalous QFT. But usually when you consider anomaly-free QFT, quantum field theory, it can be viewed as this kind of is a QFT with a symmetry with this stacking, another gapped boundary. So this may be a general picture for the anomaly-free quantum field theory. And I feel this picture is very useful. And this picture really exposes the symmetry. You know, when you can write a QFT in this way, you really expose symmetry. Mathematically, writing this way really means the partition function of this anomaly-free QFT is given by this kind of inner product of 2 partition function. Yeah, so that's the mathematical meaning of this decomposition. Yeah. And but this way you can see the symmetry more clearly. Yeah, I feel this is maybe a good way to look at the symmetry. Okay, so so basically the you know to summarize really that is the symmetry is really described by the topological order in 1 higher dimension, and this point of view may be very useful. One can use this coupled with a modular bootstrap very nicely, and we can using the modular bootstrap to study this gap and the gapless phase. Yeah. So so I try to emphasize that this is like a kind of algebraic way, or maybe number theoretical way to do quantum field theory, because we are here, we consider gapless states. We are really doing quantum field theory. But you know, when I heard quantum field theory, I'm thinking about this perturbed expansion, Lagrangian expansion, or 1 over epsilon expansion, or epsilon expansion, not 1 over epsilon expansion, and things like that. And so those like calculus is a standard techniques in quantum field theory. And but that's maybe a kind of kind of wrong direction, but that's very strong. The things that when you consider gapless state, gapless CFT, the quantum field theory is not a calculus. It's a number theory, or it's an algebra. So using calculus to look at the quantum field theory as a CFT, as a gapless point, maybe it's maybe it's wrong direction. Yeah, that's so here I really try to say that this you can see that to determine the gapless property, and the approach here really uses like some algebra, some number theory, or some category, this kind of thing, and it's a very different from perturbation. One thing is that, for example, if you want to use the epsilon expansion to compute the critical exponent, if you know the critical exponent is a rational number, there's no way to compute the rational number using perturbation expansion. Yeah. So there's certainly this big issue, that's whether the critical exponent in higher dimension, whether there's some kind of algebraic number or not. If there's some kind of algebraic number, then we should not compute them using perturbation expansion, because that's kind of a wrong approach in a sense. Yeah. So here I just try to say that there's maybe this algebraic approach, or number theoretical approach, maybe it's more fundamental. Certainly, there's many open questions, but if this is really right direction, and we are not sure at the moment, if this algebraic approach really represents the right direction, that's almost like a shift of the theory for CFT from one direction to another direction. So it's a very big shift, and so I don't know whether this kind of change of theme will happen in CFT or not. So this is a big question. Yeah, thank you very much. Yeah.
So for the S3 model, you mentioned it as a static model, right? Not constraint.
Yeah, static model is easier to simulate because the space-time are symmetric.
Yeah. But you just use some simple TRG or some loop TRG or kind of offer.
Oh yeah, non-even loop is the one we also the entanglement filtering.
There's no loop.
No loop, yeah.
Oh, in that case, maybe the syntax is not very precise.
Yeah, so that's why we kind of puzzled,
Yeah. Okay, we can try use a loop.
Yeah, I can use a loop to see whether I can get a better center charge.
Yeah.
And as I mentioned that you just this a very simple so-called entanglement filtering TRG. We get something close to 1.3.
Right,
but it shifts, and
sometimes the center charge is very tricky.
Yeah, it's very tricky. Yeah, I think at the fifth iteration is 1.3, because 10th iteration maybe became 1.1.
Yeah, it's unstable. So this loop charge you can do like up to 20 or 30.
Yeah, maybe. Yeah, that's this is one thing. So yeah, maybe you can I can go fix this point. Yeah.
Yeah. So at the end, you're talking about QFT and maybe an algebraic approach. Okay, I know there's an algebraic QFT. I haven't heard of it. I haven't studied it. It seems similar in philosophy. Do you know if it's just the philosophy that's similar, or if these algebraic quantities you're considering are the same?
It's different. Yeah. Okay. So maybe let me. But that's a very good question. And so maybe I should say the number theoretical approach, not algebraic approach.
Oh.
So what we do here really number theoretical approach. Yeah, to really and the CFT you mentioned is this is more like algebraic CFT. That's a more algebra. It's really trying to define CFT more rigorously using this operator algebra, space-like, time-like operator algebra, and but certainly this number theoretical approach and algebraic approach are also very closely related. So I feel that now it's time to go back to this algebraic approach to CFT or QFT, and maybe one can making progress, because this is a kind of the old topic, and I think in recent years there are not too many people work on that. It's very hard, and but now we have enough development. I think probably it's time to go back to this. And the point is that what I try to emphasize that we want to get a quantum field theory with no field, because at the low energy, all the quasi-particles are strongly interacting. There's nothing like a quasi-particle. So no field. And so what is the example of continuum field theory with no field? it's a CFT, conformal field theory. Again, we should delete the field. There's no quasi-particle, so there's no good field. But however, there's an algebra can specify all the structures. So hopefully that with this emphasis, we want to have the operator algebra based quantum field theory, which describes situation where field is not very useful, but this algebra is very useful. And but certainly determine the algebra, maybe one needs some number theoretical approach to determine the algebra. So these two maybe kind of combined together like this. Yeah.
I sort of have two separate, but one is regarding this maximum where you said the Ising critical because for and gauging
Yeah.
Generally, you know whether this gauging was the end, for example.
Yeah, that's a very good question. Yeah. And yeah, that's a very, very good question. And maybe let me do this. I didn't have an example here, but let me see. Yeah, here. Yeah. So for the Z2 cross Z2 symmetry, there's this kind of non-maximum condensed algebra. And it turns out, yeah, we have many of them. And they describe some kind of, for example, there's one condensed boundary described this essentially 1, CFT. Okay. And then you can say usually those CFT have additional emergent symmetry. And you can I don't know whether it's generally true or not. This additional emergent symmetry probably can be seen via this automorphism of a bulk topological order and gauging that. And you can keep gauging that. And I suspect in this case, there's no end. You can gauge to infinity. But however, this gauging to infinity, you get a sequence of a topological order. This sequence topological order I'm suspecting like this ZN gauge theory or something like in cosmology algebra problem, the U1 level n cosmology algebra with n go to infinity. So basically means that it's after all this gauging, we get a continuous symmetry, emergent continuous symmetry, U1 symmetry. So when the gauging became with no end, it's usually in some example we know things indicate the emergence of continuous symmetry. So that's another way we mentioned that we have a hard time to describe continuous symmetry because continuous symmetry corresponds to infinity category. But we can view the infinite category as a limit, as a sequence of a finite category. It means that this particular continuous symmetry allow embedding of a bunch of finite category. So we just study all their subcategory, then try to specify this infinite category. So this is like from this approach. Yeah, so basically by study all the subgroup U1, all the finite subgroup U1, we probably can determine the U1 symmetry. So this kind of interesting thing, mathematically, by study all the subgroup SU2 and their relation of subgroup, can we understand, can we completely characterize SU2, for example? So this may be representing a way, but indeed they don't stop. But on the other hand, I feel this solution they may stop. Yeah, because this middle model central charge is less than 1. So minimal discrete, when you cannot follow up. But when you're gauging, the central charge don't change. And so actually the maximum categorical symmetry for this is a double 6-5 minimal model. This one is kind of right more like more kind of glue in certain way. There's a doubled version. So but however the one with central charge bigger than 1, I'm not sure gauging would stop. But if it do not stop means it may have a continuous emergent symmetry. You have another question?
The second question I had was for the Z3 to Z2 transition.
Yeah.
Like beyond non-balance.
Yeah.
I guess usually people associate it with some anomaly, but I guess in this case you can't have them. So is that indicating something?
D3 to Z2. I don't know. It's a.
For example, like when people
Yeah, maybe there's a this. Yeah, you can see there's an anomaly because this Z2 Z3 they are not independent group. They embed in the S3 in certain way. Yeah, but I don't know whether one can describe using anomaly or not. Maybe yeah. I didn't look into that direction. Yeah, but certainly it's not just not independent Z2 and Z3. Because they embedded into S3 in a non-trivial way. There's some relation. So there's actual features to say this Z2 Z3 are coupled in some way. And yeah, we can call this actual feature anomaly. Yeah. So therefore the statement is not just an ordinary Z2 Z3 transition. Yeah. Yeah, but the Z2 Z3 are a subgroup S3. But I don't know in this case, yeah, how to describe it. May not be anomaly, but some feature. There are actual features. Basically means that if you view Z2, Z3 together, you don't get Z2, Z3, you get S3. This actual feature make that happen. So that means these two Z2, Z3 have some non-trivial twist between them. Yeah.
This seems to suggest that, like, in general, for group with full symmetric groups, there are group extensions that's like one by another.
Yeah.
And that group extension is like non-trivial, let's say, sometimes.
Yes.
That would require you to use this kind of like position that giving that easier legitimate generalization.
Yeah, maybe this. Yeah, so this S3 is some group extension of maybe Z3 by Z2, something like that. And yeah, maybe non-trivial group extension means they have a non-trivial relation. Yeah. So yeah, maybe there's maybe some kind of, I don't know, Tuchel cycle describing this non-trivial thing. Yeah, there's something along that direction indeed. Yeah.
Do you think these setback models might be non-integrable?
What?
That these setback models that you write down, like S3 to Z1, for example,
that
they are non-integrable?
I don't know. Yeah. What you write down is pretty arbitrary. So
mostly where you write down.
Yeah, probably not integral, but I don't know whether there's some nicer way. Yeah, we didn't explore that direction. Whether there's some nicer way to write down the S3 model, which may be more integral, but also allow all the four phases. The thing that I think post model is integrable, but that's only allow two phases, Z3 and Z2, S3 and Z2. But whether there's an integral model which allow all the four phases, that is the issue. Okay, yeah, I can end here. Thank you for coming.